There is a limit to how much energy the universe will allow you to focus into a single point. Not a technological limit, not a human one, but a boundary written into reality itself, where space and time stop behaving like the smooth, continuous stage we know. At that edge, energy becomes so concentrated that distance loses meaning, clocks lose rhythm, and the familiar fabric of space-time begins to tear. This boundary has a name: Planck Energy. And tonight, we will approach it slowly, carefully, without rushing, as if lowering ourselves into very deep water. If this quiet journey brings you even a moment of calm or wonder, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these peaceful explorations alive, and it truly means more than you know. Now, let's begin with the first truth. Part 1. At what point does energy stop being gentle? There is energy everywhere around you right now, in the warmth of your skin, in the slow movement of air, in the faint glow of distant stars arriving after traveling for millions of years. Most of the time, energy is quiet, spread out, harmless. But physics tells us that energy changes character when it is compressed. As you concentrate more and more energy into smaller and smaller spaces, something fundamental begins to shift, and the universe responds in ways that are both precise and unforgiving. To understand this shift, it helps to begin with something familiar. Think of energy as something that prefers room. Heat spreads out, light fans across space, sound fades as it travels. In everyday life, energy dissipates naturally, flowing from crowded places into emptier ones. This tendency toward spreading is why a hot cup of tea cools, why a bright lamp softly fills a room, and why motion eventually slows. Energy left alone is gentle because it is diluted. But physics allows energy to be gathered, focused, confined, and when it is, its behavior changes. If you hold a magnifying glass under sunlight, you already know this. Spread across a wide area, sunlight feels warm but safe. Focused into a tiny point, that same sunlight can scorch paper. Nothing about the light itself changed, only its concentration. This simple experiment hints at a much deeper truth. Energy density matters more than energy alone. As scientists learned to probe smaller and smaller scales, they discovered that seeing detail requires energy. Not just more energy, but energy packed tightly together. To resolve fine structure, you need waves with short wavelengths. Shorter wavelengths demand higher energy. This is not a technological choice. It is a law of nature. At the scale of atoms, gentle light is no longer enough. Visible light has wavelengths far too large to distinguish individual atoms. To look closer, physicists turn to more energetic forms of probing. Electrons, X-rays, particle beams accelerated to enormous speeds. Each step inward required energy that was not only higher, but more sharply, confined in space and time. At first, this increase seems manageable. Electrons scatter, atoms reveal structure, protons show internal components, nature appears cooperative. But beneath this cooperation lies a growing tension. Energy does not exist separately from gravity. This is one of the most subtle lessons of modern physics. According to Einstein, energy and mass are interchangeable. Energy has weight, it curves space. Even a beam of light, though massless, contributes to gravity because it carries energy and momentum. When energy spreads out, its gravitational effect is negligible. But when energy is compressed, gravity quietly awakens. Imagine continuing to zoom in. Each attempt to see smaller details requires more energy squeezed into a smaller region. The act of observation itself becomes more forceful. The energy you use to look begins to alter the space you are trying to observe. Geometry bends, distances shift, time itself responds. At ordinary scales, this effect is far too small to notice, but physics is patient. If you keep pushing, the equations tell a clear story. There exists a threshold where energy density becomes so extreme that gravity can no longer be ignored. At this point, space does not merely curve gently, it collapses inward. The energy you concentrated creates a gravitational well so deep that even light cannot escape. A horizon forms. This is the moment energy stops being gentle. What makes this moment remarkable is that it is not associated with stars or galaxies. It emerges purely from concentration. You do not need enormous total energy. You only need enough energy in a small enough volume. Gravity cares about density, not scale. This realization transformed how physicists think about limits. It revealed that the universe is not infinitely willing to reveal its smallest structures. At some point, the tools used to see deeper destroy access rather than enhance it. Observation becomes obstruction. This boundary is not arbitrary. It is defined by a natural scale where the fundamental constants of nature converge: the speed of light, the strength of gravity, the quantum of action. When these constants are combined, they define a characteristic energy, length, and time. At these scales, the familiar categories of physics dissolve. Below this threshold, energy behaves as something we can manipulate, guide, and measure. Above it, energy becomes geometry. It reshapes the stage itself. You can think of this boundary as the universe's way of enforcing balance. The more aggressively you try to interrogate reality, the more reality pushes back. Not with chaos, but with structure, horizons, limits, silence. What is especially calming about this realization is its inevitability. No civilization, no matter how advanced, can bypass this boundary by clever engineering alone. It is not a failure of imagination or technology. It is woven into the architecture of existence. This means that the deepest layers of reality are not chaotic free-for-alls. They are protected, guarded by the same laws that allow stars to shine and planets to orbit. Energy, when allowed to spread, creates warmth and light. When forced into confinement, it creates gravity and boundaries. In this sense, the universe favors gentleness by default. Extremes require effort, and those efforts are met with resistance. As you sit here now, breathing slowly, consider how much energy moves through your body every second. Chemical reactions, electrical impulses, thermal motion, all of it flowing smoothly because it is distributed. None of it concentrated enough to disturb the fabric of space beneath you. This balance is what allows calm to exist at all. The lesson of this first part is not about danger or destruction. It is about thresholds, about the quiet transition from one regime of physics to another, about how energy, the same energy that warms your hands and lights distant galaxies, can under the right conditions bend time, seal information, and draw invisible lines across reality. And as we continue this slow journey inward, one question remains gently suspended in the air. If energy becomes gravity when compressed far enough, and gravity reshapes space and time, then what happens to space itself when we try to look beyond those limits? That question is where we drift next. Part 2. Why seeing smaller always requires more energy. If you could keep zooming in forever, past cells, past atoms, past even the particles inside the nucleus, would the universe continue revealing finer detail? Or would it resist? Every microscope ever built follows the same rule. To see smaller things, you must use higher energy. This is not a human invention. It is a law woven into waves, particles, and light itself. And with each increase in energy, observation becomes less gentle and more disruptive. This rule begins quietly, almost invisibly, in the nature of waves. Light, sound, and even matter itself behave as waves under the right conditions. And every wave carries a defining property: wavelength, the distance between its peaks. This single number determines how much detail the wave can reveal. A wave cannot resolve structures smaller than its own wavelength. It simply flows around them. This is why ocean swells pass over submerged rocks without disturbance, and why low-frequency sound bends around walls. Detail disappears when the wave is too large. Light obeys the same rule. The soft light that fills a room has wavelengths hundreds of nanometers long. At that scale, atoms are invisible. No matter how perfect a glass lens becomes, visible light will never show individual atoms. It is not a limitation of craftsmanship. It is a boundary set by physics. To see smaller, you need shorter wavelengths, and shorter wavelengths require higher energy. This relationship is precise and unavoidable. In quantum physics, the energy of a photon is inversely proportional to its wavelength. Halve the wavelength, and you double the energy. Shrink it further, and the energy rises sharply. There is no workaround. Resolution is purchased with energy. At first, this trade seems reasonable. When scientists wanted to see cells, visible light was enough. When they wanted to see viruses, they turned to ultraviolet. When they sought atomic structure, they used X-rays. Each step inward demanded more energetic probes, and each step revealed astonishing new layers of reality. But something subtle happened along the way. As energy increased, observation stopped being passive. High-energy light does not merely reflect, it interacts, it excites electrons, it breaks bonds, it alters the very systems it tries to measure. At atomic scales, observation begins to leave fingerprints. This is where the act of seeing becomes an act of disturbance. To look inside an atom with visible light is impossible. To look with X-rays is possible, but dangerous. X-rays carry enough energy to ionize atoms, stripping electrons away. They reveal structure, but they also change it. The image you obtain is never fully innocent. To reduce this damage, physicists turn to particles instead of light. Electrons, though massive, also behave as waves, and because their wavelength depends on their momentum, electrons can achieve extremely short wavelengths at relatively modest energies. This made electron microscopes possible, allowing humanity to see individual atoms for the first time. Yet, even here, the rule persists. To see smaller still, electrons must be accelerated to higher energies, and higher energy electrons punch deeper, scatter more violently, and disrupt the structures they encounter. There is no regime where seeing becomes free. This is not because nature is unkind, but because information itself has a cost. To resolve small distances, you must localize interactions. Localization requires momentum. Momentum requires energy. And energy, when confined, exerts influence. As physicists push deeper, probing the nucleus and beyond, this cost grew steeply. Probing protons required particle accelerators. Seeing inside protons required energies millions of times greater than those used in electron microscopes. Each increase brought new discoveries, but also new complications. Particles did not behave like solid beads. They fragmented, they fluctuated, they transformed into showers of other particles. The deeper scientists looked, the less stable the picture became. This instability is not accidental. At high energies, quantum fields awaken. Empty space is no longer empty. It becomes active, capable of producing particles, fluctuations, and fleeting structures. The vacuum itself begins to participate. Seeing smaller does not simply reveal static layers, it reveals motion, and motion at these scales is inseparable from uncertainty. Quantum mechanics tells us that attempting to localize a particle precisely requires large momentum uncertainty. The more tightly you pin something down, the more violently it resists. This is not a flaw in measurement, it is a property of reality. The Heisenberg uncertainty principle is often misunderstood as a statement about imperfect instruments, but it is deeper than that. It tells us that nature does not permit unlimited precision without consequence. Energy rises as certainty increases. As you push resolution toward smaller distances, uncertainty spills outward. Particles jitter, fields fluctuate, events blur. At nuclear scales, this uncertainty is manageable. At subnuclear scales, it dominates. And beyond a certain point, it collides with gravity itself. This is where the story bends, because gravity too responds to energy. As observation energy rises, it does not remain an abstract number. It curves space, it slows time, and if confined enough, it creates horizons that block information entirely. This means that the universe does not offer an infinite ladder of detail. It offers a staircase that ends. The requirement of higher energy to see smaller is not just an inconvenience. It is the mechanism by which the universe protects its deepest structure. Each step inward becomes more disruptive, more costly, more resistant. Eventually, the cost exceeds the benefit. What makes this realization so profound is that it reframes curiosity itself. The universe is not hiding out of secrecy. It is hiding through consistency. The same rules that allow us to see stars also prevent us from dissecting spacetime without consequence. There is a quiet symmetry here. Large structures are visible because they are gentle. Small structures are hidden because they are intense. The universe reveals what can be observed without being destroyed. As you rest here now, think about the scale at which your senses operate. Your eyes see light that has traveled vast distances, carrying information without harm. Your ears hear pressure waves that dissipate harmlessly in air. Your body exists at an energy scale that allows stability, memory, and calm. This is not accidental. Life exists in a narrow window where energy is high enough to sustain complexity, but low enough to remain gentle. Too little energy, and nothing moves. Too much, and nothing holds together. The requirement that seeing smaller demands more energy is a reminder of this balance. Knowledge is not free. It has a physical price, and at the smallest scales, that price becomes absolute. As physicists continue to explore the boundaries of resolution, they do so knowing that the universe will not yield infinitely. At some point, the act of seeing becomes indistinguishable from the act of creating. And that leads us naturally to the next question, waiting just beyond this threshold. If increasing energy makes observation disruptive, and if light itself becomes destructive at high energies, then what exactly happens when light grows too powerful to be used as a tool at all? That is where we turn next. Part 3. When light becomes too powerful to look with light, feels soft to us. It illuminates without touching. But at high enough energies, light stops being a passive messenger and becomes an active force. Photons shrink in wavelength as their energy rises, and when they grow too energetic, they no longer reveal structure, they destroy it. At a certain point, light is no longer a window into reality. It becomes a hammer, striking the very thing it tries to observe. For most of human history, light was the gentlest tool we knew. It arrived silently. It carried images across empty space. It let us see without interference. Even today, when you open your eyes, it feels as though the world simply offers itself up, calmly, without cost. But physics tells a more careful story. Light is not just illumination. It is energy in motion. Each photon carries a precise amount of energy determined by its frequency. Low-frequency light, like radio waves, stretches gently across kilometers of space. Visible light compresses into much shorter waves, and beyond that, ultraviolet, X-rays, and gamma rays compress further still, carrying energy dense enough to change matter. This compression is the key. As wavelength shrinks, energy rises, and as energy rises, interaction becomes unavoidable. At low energies, photons mostly bounce. They scatter gently from surfaces, transferring almost no momentum. This is the regime where light behaves like a polite guest, asking permission before passing through. But increase the energy, and the interaction sharpens. Ultraviolet photons can break molecular bonds. This is why sunlight can tan skin or damage it. The photons are energetic enough to rearrange chemistry. They no longer just show you a surface, they alter it. X-rays go further. They penetrate deep into matter, passing through flesh while interacting strongly with denser materials like bone. But in doing so, they ionize atoms, knocking electrons loose. This process is useful for imaging, but it comes at a cost. Each X-ray photon leaves a trail of disruption behind it. Gamma rays push beyond even that. At these energies, photons can pass through entire planets with only a small chance of interaction. But when they do interact, the effects are violent. They can shatter nuclei, create particle-antiparticle pairs, and deposit energy so abruptly that matter itself recoils. This progression reveals a quiet truth. Light becomes less informative as it becomes more forceful. At high energies, the act of illumination is indistinguishable from the act of impact. This creates a paradox for observation. To see smaller structures, light must become more energetic. But the more energetic it becomes, the more it interferes. Eventually, the light overwhelms the very structure it is meant to reveal. This is not a failure of technique. It is a fundamental trade-off. Even when scientists use the most carefully tuned beams, this trade-off remains. At atomic scales, photons can excite electrons out of their natural states. At nuclear scales, photons can destabilize entire nuclei. The deeper you try to look, the more the object resists by changing. This resistance is not conscious, but it is consistent. Nature does not allow itself to be observed without consequence at extreme scales. There is another layer to this story, quieter but equally important. Photons do not only interact with matter, they interact with space-time itself. According to general relativity, any form of energy curves space. A single photon's effect is unimaginably small. But as photons become more energetic, and as they are packed into smaller regions, their collective influence grows. A beam of intense light has gravity. This sounds abstract, but the equations are clear. Energy contributes to the stress-energy tensor, the source of space-time curvature. Enough concentrated light can, in principle, bend the geometry around it. This leads to an unsettling implication. If you continue increasing the energy of light to probe ever smaller distances, you eventually reach a point where the gravitational effect of that light cannot be ignored. The photons begin to curve the space they travel through. The path of observation bends inward. At the extreme limit, the light you use to look creates a gravitational trap so strong that it cannot escape. Your window closes. This is the ultimate transformation of light from messenger to barrier. At this scale, light no longer brings information outward, it seals information in. This is where the idea of a minimum length enters physics. A distance so small that attempting to resolve it with light requires so much energy that the region collapses behind a horizon. Below this scale, the concept of looking loses meaning. Light does not fail here because it is weak. It fails because it is too strong. What is remarkable is how universal this limit is. It does not depend on technology, material, or ingenuity. It emerges from the constants of nature themselves, the speed of light, the gravitational constant, the quantum of action. Together, they conspire to enforce this boundary. This tells us something profound about the universe's character. Reality is not infinitely transparent. It has opacity built into its foundation. At human scales, this opacity is invisible. Light feels effortless, seeing feels free. But at extreme energies, transparency gives way to protection. The universe preserves its deepest structure by making it inaccessible to forceful probing. There's something almost gentle in this refusal. Instead of allowing infinite dissection, nature responds with horizons. Instead of chaos, it offers silence. As you rest now, notice how light behaves around you. It fills the room softly. It reflects off surfaces without resistance. It carries images without disturbance. This is light at a scale where energy is shared generously, spread thinly across space. This gentleness is what allows calm perception. The same light, concentrated billions of times more intensely, would behave very differently. It would burn, disrupt, and bend the geometry beneath it. Not because it is evil or dangerous, but because energy density demands consequence. This dual nature of light mirrors a broader truth about knowledge itself. Gentle inquiry reveals, forceful inquiry distorts. At some point, understanding requires restraint. Physicists have learned this lesson repeatedly. Each advance into higher energies brings incredible insight, followed by new limits. The universe rewards curiosity, but only up to a point. Beyond that, it insists on balance, and this insistence is not arbitrary. It is the same principle that allows stars to shine without collapsing instantly. It is the same balance that allows atoms to exist without flying apart. It is the same moderation that allows time to flow smoothly for you now. Light becomes too powerful to look with not because we misuse it, but because power itself reshapes the conditions of observation. As we continue this quiet descent, the next question arises naturally, almost inevitably. If light, the fastest and most trusted messenger in the universe, becomes destructive at extreme energies, then what happens when observation itself begins to bend space and time? That question carries us forward, deeper into the place where gravity and quantum physics begin to speak at the same time. Part 4. The Quiet Collision. Between quantum physics and gravity. Quantum mechanics governs the small. Gravity governs the massive. For most of the universe, these two theories live separate lives, never interfering with one another. But as energy density rises, they are forced into the same space, and when they meet, their rules disagree. Quantum uncertainty demands fluctuation, gravity demands structure. The closer you push toward extreme energy, the louder this disagreement becomes. For nearly a century, these two pillars of physics have coexisted peacefully by staying apart. Quantum mechanics describes atoms, particles, probabilities, and uncertainty with extraordinary precision. Gravity, through general relativity, describes planets, stars, galaxies, and the slow curvature of space and time with equal success. Each theory works beautifully in its own domain. The problem is not that either theory is wrong. The problem is that the universe does not respect the boundary between small and massive. As long as energies remain modest, quantum effects dominate the microscopic world, and gravity remains too weak to matter. As long as masses are large and spread out, gravity shapes the cosmos while quantum fluctuations average away into insignificance. This separation allows physicists to calculate, predict, and understand vast ranges of reality without conflict. But there are places where this separation fails. Whenever energy becomes extremely concentrated, size and mass stop being independent concepts. Quantum particles carry energy. Energy carries gravity. And suddenly, the small becomes heavy. This is where the collision begins. Quantum mechanics insists that at very small scales, nothing is fixed. Particles do not sit still. Fields fluctuate. Even empty space trembles with uncertainty. The vacuum is alive with transient activity, particles appearing and disappearing too quickly to be directly observed. This restless motion is not noise. It is the natural state of quantum reality. Gravity, on the other hand, insists on smoothness. It treats space and time as a continuous fabric that bends predictably in response to mass and energy. In general relativity, space-time does not jitter, it curves. These two demands cannot both be satisfied when energy density becomes extreme. As you compress energy into smaller and smaller regions, quantum mechanics demands increasing uncertainty in position and momentum. The region becomes fuzzier, less defined, more restless. At the same time, gravity responds by curving space-time more sharply, attempting to create a stable geometric structure around the energy. One theory wants motion without boundaries. The other wants boundaries without motion. This disagreement grows louder as scales shrink. At atomic energies, gravity is so weak that its voice is inaudible. At nuclear energies, it is still negligible. But continue increasing energy, and gravity's influence rises steadily. Eventually, it cannot be ignored. This happens not because gravity becomes stronger, but because energy density does. There is a particular scale where this conflict becomes unavoidable. At this scale, the quantum fluctuations of space-time itself become significant. Space is no longer a passive stage where particles act. It becomes part of the quantum system. The idea is unsettling. In quantum mechanics, particles exist in superpositions. They do not have single definite positions until measured. If space-time itself becomes subject to quantum uncertainty, then distance, duration, and geometry lose their classical meaning. The very coordinates we rely on to describe events begin to fluctuate. General relativity cannot accommodate this. Its equations require a smooth, well-defined geometry. They assume that space-time exists first and matter moves within it. Quantum mechanics reverses this logic, allowing matter and energy to define reality probabilistically. This is the heart of the collision. Neither theory is willing to yield. Physicists have tried to reconcile them for decades. They have proposed quantum versions of gravity, discrete units of space, vibrating strings, looping geometries, and emergent dimensions. Each attempt captures part of the truth, but none has yet fully resolved the conflict. What is clear is this: when quantum physics and gravity meet, space-time itself becomes unstable. This instability does not manifest as explosions or chaos in the everyday sense. Instead, it appears as a breakdown of description. Our equations stop agreeing, predictions lose certainty, concepts like before and after blur. At this boundary, asking where something is becomes meaningless. Asking when something happens becomes ambiguous. The language of classical physics simply no longer applies. And yet, this breakdown is not random. The conflict arises in a very specific way, at a very specific scale. The same constants that govern light, gravity, and quantum action conspire to define where this collision occurs. This suggests that the universe has a built-in transition point where one description of reality hands off to another. This handoff is not violent. It is quiet. There is no signal, no warning, no dramatic event. The equations simply stop cooperating. The universe does not explode. It becomes silent to our questions. This silence is often misunderstood as ignorance, but it is better understood as boundary. Think of it like sound fading as you move underwater. The air does not vanish. Your ability to use it does. The medium changes, and your tools no longer work the same way. At the quantum gravity boundary, our tools fail not because reality breaks, but because it changes character. What makes this boundary so fascinating is that it is not merely theoretical. The early universe passed through this regime. In the first instance after the beginning, energy densities were so high that quantum fluctuations and gravity were inseparable. Space and time themselves were likely subject to quantum uncertainty. This means that the universe we see today emerged from a state where neither quantum mechanics nor general relativity alone could describe reality. Everything you experience now, distance, duration, causality, condensed out of that uncertain beginning. In a sense, the calm structure of space-time you inhabit is a cooled-down version of something far more restless. As the universe expanded and energy spread out, gravity softened, quantum fluctuations averaged away, space settled into a smooth geometry, time acquired a direction, the conflict quieted, but it never vanished completely. Even now, in places where energy becomes extreme, near black holes, in the hearts of neutron stars, in the highest energy particle collisions, the whispers of that ancient disagreement return. Our theories strain, our predictions wobble, and this is not a failure. It is a clue. It tells us that our understanding is layered, that reality does not belong to a single framework, that nature allows different rules to dominate at different scales and refuses to be simplified into one language too early. There is something profoundly calming in this. The universe does not demand that we understand everything at once. It allows approximation, it allows perspective, it allows mystery without collapse. As you breathe quietly now, consider how little of this conflict touches your daily life. Gravity holds you gently to the earth. Quantum mechanics governs the chemistry in your body. They coexist peacefully here, each operating where it is best suited. Only at the edges do they argue, and those edges are far from where life unfolds. This tells us something important about stability. The universe is constructed so that extreme conflicts occur only at extreme scales. The conditions required to force quantum mechanics and gravity into direct confrontation are rare, costly, and difficult to achieve. That rarity is what allows stars to burn steadily, planets to orbit calmly, and minds like yours to rest. As we continue this journey, one more question rises naturally from this collision. If energy density can force quantum uncertainty and gravitational structure into conflict, what happens when gravity finally wins? When energy becomes so dense that space-time itself collapses into something from which nothing can escape? That question carries us forward toward the moment where energy does not just bend space, but seals it shut. Part 5. What happens when energy gains weight? Einstein revealed a subtle truth. Energy and mass are interchangeable. Energy has weight. It bends space. When energy becomes dense enough, it doesn't just illuminate or excite particles, it curves the geometry around it. At first, the curvature is small, almost imperceptible. But with enough energy packed tightly together, space-time itself begins to fold inward. This idea is easy to miss, because in daily life, energy feels weightless. Light pours through windows without pressing down. Heat rises and dissipates. Electricity flows silently through wires. None of it feels heavy. None of it seems capable of shaping the world in the way a mountain or a planet does. But physics tells us that this is an illusion of scale. In Einstein's view of the universe, gravity is not a force pulling objects through space. It is the shape of space itself responding to energy and mass. Anything that carries energy contributes to this shape, not just stars and planets, but light, pressure, motion, and heat. All of it counts. This is written precisely into the equations of general relativity. The source of gravity is not mass alone, but something called the stress-energy tensor. It includes energy density, momentum, pressure, and even tension. In this framework, energy is never passive. It always participates in shaping the universe. Most of the time, its influence is too small to notice. A single photon does bend spacetime, but the effect is so tiny that it disappears beneath every other influence. A beam of light crossing a room adds gravity, but the curvature it creates is many orders of magnitude below anything measurable. Space remains, for all practical purposes, flat. But the equations do not forget. They keep count, no matter how small the contribution. As energy becomes more concentrated, its gravitational influence grows. This growth is not linear. It accelerates. Each increase in energy density deepens curvature more sharply than the last. And because curvature affects how energy moves, a feedback loop begins to form. This feedback is gentle at first. Imagine placing a small weight on a stretched fabric. The fabric dips slightly. Roll a marble nearby, and it curves inward just a bit. Now imagine adding more weight, concentrated into a smaller point. The dip deepens, the slope steepens. The marble accelerates more quickly toward the center. Space-time behaves in much the same way. As energy density rises, the curvature steepens. Paths bend more strongly. Time slows relative to distant observers. Light itself begins to follow curved trajectories. At moderate densities, this curvature gives us familiar phenomena. Planets orbit stars. Light bends around galaxies. Time ticks more slowly near massive objects. All of this has been measured, confirmed, and quietly folded into our understanding of reality. But these are still gentle regimes. The real transformation happens when energy density crosses a critical threshold. At that point, curvature no longer simply guides motion, it traps it. This threshold does not depend on what the energy is made of. It does not care whether the energy comes from matter, radiation, or motion. Gravity responds only to how much energy exists within a given volume. If enough energy is confined inside a small enough region, space-time folds inward so steeply that nothing can climb back out. Not particles, not light, not information, a boundary forms. This boundary is what we call an event horizon. What makes this remarkable is that the formation of such a horizon does not require exotic ingredients. It does not require collapsed stars or cosmic catastrophes. It requires only sufficient energy density. In principle, any form of energy can create one if it is compressed enough. This realization reframes black holes entirely. They are not objects in the traditional sense. They are regions where energy has gained so much gravitational influence that space-time itself closes around it. The horizon is not a surface, it is a geometric condition, a point of no return defined by curvature. From far away, the energy inside continues to exist, its gravitational pull remains, but the details are sealed away. This sealing is absolute. Once energy gains enough weight to form a horizon, the universe enforces silence. Information cannot escape. Causes inside cannot affect effects outside. Space and time themselves rearrange to enforce this separation. This is gravity's final word. What is striking is how smoothly this transition occurs. There is no alarm, no sudden violence at the boundary. An observer falling inward would notice nothing special at the horizon itself. Locally, physics behaves normally. It is only from afar that the barrier becomes evident. This quietness is a theme repeated throughout nature. The most dramatic transitions often occur without spectacle. They are written into geometry, not fireworks. As energy gains weight, time responds as well. Clocks near concentrated energy tick more slowly. This is not metaphorical. It is literal. Time stretches, processes slow. From the outside, motion near dense energy appears frozen. This time, dilation is not a side effect. It is inseparable from curvature. Space and time are woven together. Bend one and the other follows. As energy density increases, this weaving tightens. Paths through space-time become steeper. Options narrow. Futures converge. At the extreme, time itself points inward. This is perhaps the most unsettling consequence of energy gaining weight. Inside a horizon, moving forward in time means moving deeper inward. Escape is not forbidden by force, it is forbidden by geometry. There is no path that leads outward because outward no longer exists as a future direction. This is not intuitive, but it is consistent. It tells us that gravity, when pushed far enough, reorganizes reality itself. And yet, even here, there is restraint. The universe does not allow energy to collapse arbitrarily. Quantum mechanics resists confinement. Uncertainty grows. Fluctuations intensify. As we explored earlier, quantum effects push back against gravity's desire for structure. This pushback delays collapse. It complicates it. It introduces thresholds rather than inevitabilities. Only when energy density overwhelms this resistance does gravity complete its folding. This balance between resistance and collapse is what defines the deepest limits of observation. It is why attempting to probe extremely small distances with extremely high energy leads not to clarity, but to horizons. The act of investigation becomes the act of sealing. There is something almost philosophical in this outcome. The universe allows energy to illuminate, to warm, to build, and to move freely across vast scales. But when energy is forced into extremes, it transforms from messenger to architect, from information carrier to geometric sculptor. At that point, knowing becomes impossible not because of ignorance, but because of structure. As you lie quietly now, the energy around you remains gentle. It flows, disperses, and balances itself. The gravitational influence of that energy is present, but calm. Space remains open. Time moves steadily forward. This gentleness is not accidental. It is the natural state of a universe that favors distribution over confinement. Energy only gains dangerous weight when it is denied room. And this leads us gently to the next question, waiting just beyond the curve of space-time. If energy, when compressed enough, can fold space inward and create horizons, then what happens at the precise moment when observation itself collapses behind that boundary? That is where we turn next, toward the instant when seeing becomes impossible and the universe quietly draws the line. Part 6. The moment a measurement turns into a horizon. There is a point where observation becomes impossible, not because of poor instruments, but because nature draws a line. When enough energy is confined to a tiny region, gravity becomes so intense that even light cannot escape. A horizon forms, not at the center of a star, but inside the act of measurement itself. Beyond this boundary, information is sealed away forever. This idea feels strange at first because we are used to thinking of horizons as distant astronomical things, the edge of a black hole, the boundary of a collapsing star, something vast and far removed from the quiet act of looking. But physics tells us that horizons are not defined by size or location. They are defined by energy density and geometry. A horizon is simply the place where escape stops being possible. And that place can appear anywhere, even inside an experiment. To see how this happens, return again to the simple act of measurement. When you try to observe something very small, you must localize energy into a very small region. You focus a beam, you accelerate a particle, you increase momentum. Each of these steps concentrates energy into space and time. At modest energies, nothing dramatic happens. The system responds. Particles scatter, signals return. Information flows outward, carrying answers with it. Measurement succeeds. But as the scale shrinks and the energy rises, the rules quietly begin to change. Gravity does not announce itself loudly. It does not interrupt the experiment. It does not create noise or resistance. It simply curves space a little more with each increase in energy density. At first, this curvature is negligible. Then it becomes noticeable. Then it becomes dominant. At a certain threshold, the geometry becomes so steep that outward paths vanish. This is the moment the measurement becomes its own horizon. What makes this profound is that nothing has gone wrong. The apparatus functions exactly as designed. The energy is delivered precisely. The target is localized perfectly. And yet, no signal returns. Not because the signal failed, but because the geometry no longer permits escape. Light itself cannot climb out. At this point, the experiment has not failed. It has succeeded too well. The act of observation has crossed a fundamental boundary. By attempting to extract information from an extremely small region, it has created a region from which information cannot escape at all. This is not a technological limitation. No refinement can fix it. No clever workaround can bypass it. The boundary is enforced by space-time itself. Physicists sometimes describe this as the universe protecting its smallest scales. But it is not protection in an intentional sense. It is a consequence of consistency. Gravity cannot be turned off. Energy cannot be weightless. Geometry must respond. When energy density exceeds a certain point, horizons are inevitable. This inevitability reframes how we think about knowledge. It suggests that some questions cannot be answered not because they are poorly formed, but because answering them would require conditions that erase the possibility of answers. In other words, the universe does not forbid us from asking. It simply ensures that some answers cannot be returned. There is a quiet elegance to this. Nature does not collapse into paradox. It resolves conflict by sealing it off. Where quantum uncertainty grows too wild and gravity grows too strong, space-time reorganizes itself into a configuration that enforces silence. The horizon is not a wall, it is a rule. Inside it, physics continues. Energy still exists. Processes still unfold, but none of that can influence the outside world. The horizon divides reality into regions that can communicate and regions that cannot. This division is absolute. What is especially striking is that this same mechanism appears at vastly different scales. It governs black holes millions of kilometers across, and it governs hypothetical experiments probing distances trillions of times smaller than an atom. The mathematics does not care about size, only about density. This tells us that horizons are not exotic anomalies. They are natural outcomes of extreme concentration, and concentration is exactly what measurement demands at the smallest scales. As we discussed earlier, to see smaller details, you must use higher energy. To localize that energy, you must confine it. To confine it enough, you eventually cross the threshold where gravity responds decisively. At that moment, the experiment stops being an observation and becomes a boundary. From the outside, it looks like failure. From the inside, nothing special happens at all. This duality is one of the most unsettling aspects of horizons. They are not marked by events, they are marked by perspective. An observer far away sees signals slow, redden, and fade. Time appears to stretch endlessly at the edge. Information seems frozen, never quite crossing the boundary. The horizon becomes a surface of infinite delay. But for anything crossing inward, there is no pause, no alarm, no sudden darkness. Physics continues smoothly. The horizon is crossed without drama. This tells us that the boundary is not a physical object. It is a difference in causal structure, a difference in which events can influence which others. When measurement turns into a horizon, it is not that the thing you are measuring disappears. It is that its answers are no longer part of your future. This realization forces a subtle shift in how we understand limits. The smallest scales of reality are not hidden behind complexity or randomness alone. They are hidden behind causality itself. You cannot receive information that has no path to reach you. This is perhaps the most fundamental limitation of all. It means that the universe's deepest structure may exist, evolve, and obey laws that are perfectly consistent, yet remain forever inaccessible to any observer outside. And that inaccessibility is not due to ignorance, it is due to geometry. There is something almost comforting in this. The universe is not teasing us with unreachable secrets. It is simply operating within rules that preserve coherence. Allowing unlimited access to arbitrarily small scales would destabilize reality itself. Horizons prevent that. They act as pressure valves. They allow energy to concentrate without tearing the universe apart. They isolate extremes so that the rest of reality can remain calm, predictable, and habitable. Without horizons, extreme energy densities would leak influence outward, disrupting everything. With horizons, those extremes are contained. This containment is what allows stars to collapse without destroying galaxies. It is what allows the early universe to cool into structure. It is what allows curiosity to exist without annihilation. As you lie quietly now, consider how far removed you are from these extremes. The energy around you is spread thinly. Gravity is gentle. Space is open. Time flows smoothly. Information moves freely. This calm is not the absence of extremes. It is the result of their isolation. Somewhere in the universe, energy is dense enough to seal itself away. Somewhere, horizons quietly exist, doing their work without spectacle. And somewhere at the smallest imaginable scales, the same mechanism prevents infinite division. The moment a measurement turns into a horizon is the moment the universe says, gently but firmly, no further. Not as punishment, not as refusal, but as balance. And as we continue this journey inward, one question remains softly unanswered. If horizons appear whenever energy density becomes extreme, then what scale defines the absolute boundary of meaningful measurement itself? That question leads us next to a number so small and so precise that it marks the edge of all physical meaning. Part 7. Introducing the Planck Energy. Threshold Planck energy is not just a large number, it is a dividing line. It represents the amount of energy required to probe distances so small that spacetime can no longer remain smooth. At this scale, the familiar idea of location breaks down. Distance flickers, time stutters, and the universe refuses to be measured in the ways we're used to. To understand why this threshold matters, it helps to step back and ask a quiet question. How does the universe decide what is measurable at all? Not what is difficult or expensive or technologically distant, but what is physically meaningful. At ordinary scales, we assume space is continuous, that between any 2 points there is always another point. That distance can be divided forever. But physics does not guarantee this assumption. It only tolerates it up to a point. The Planck energy marks where that tolerance ends. This threshold emerges when the deepest constants of nature are brought together. The speed of light, which sets the ultimate limit on how fast information can travel. The gravitational constant, which determines how strongly energy bends space. And the quantum constant, which governs how finely reality can be divided into action. When these constants are combined, they define a characteristic energy scale, not chosen, not arbitrary, simply implied. At energies below this scale, spacetime behaves as something smooth and continuous. Measurements make sense. Distances can be compared. Clocks can be synchronized. The universe offers itself up in stable coordinates. But as energy approaches the Planck threshold, this smoothness begins to fail. Attempting to probe distances that small requires concentrating extraordinary amounts of energy into an extraordinarily tiny region. And as we've seen, energy confined that tightly cannot remain passive. It becomes gravitational. It distorts the geometry it inhabits. It introduces uncertainty not just in particles, but in space itself. At this point, space is no longer a fixed stage. It becomes an actor. The Planck energy is the point where spacetime is forced to acknowledge its own quantum nature. Below this threshold, quantum effects act on matter and fields within space. Above it, space joins the quantum system. Its geometry fluctuates, its structure trembles, its continuity dissolves. This is not speculation. It follows directly from combining the principles we already trust. Quantum mechanics insists that confining energy to smaller regions increases uncertainty. General relativity insists that concentrating energy increases curvature. Together, they imply a scale where uncertainty and curvature overwhelm the concept of a well-defined location. At the Planck threshold, asking where something is becomes meaningless. Not because we lack precision, but because Where no longer has a stable definition. Distances flicker. 2 points that seem separate in one moment blur together in the next. Space behaves less like a grid and more like a restless surface, constantly reshaping itself under quantum influence. Time joins this instability. At ordinary energies, time flows smoothly, even if it flows at different rates depending on gravity and motion. At the Planck scale, time cannot be cleanly separated from uncertainty. Events no longer occur in a well-ordered sequence. The idea of before and after becomes ambiguous. This does not mean that time stops. It means that time loses its familiar structure. The Planck energy threshold is therefore not just about smallness, it is about coherence. It marks the scale at which the universe can no longer maintain a single, shared framework for measurement. Below this scale, observers can agree on distances and durations, even if they disagree on details. Above it, agreement itself becomes impossible. This is why the Planck threshold is often described as the smallest meaningful scale. Not the smallest imaginable one, but the smallest one that physics can consistently describe. Beyond it, our language breaks down. Importantly, this breakdown is not chaotic, it is systematic. The equations do not explode, they simply stop yielding definite answers. Predictions turn into ranges, coordinates turn into probabilities, geometry becomes statistical. This suggests that the Planck threshold is not a cliff, but a fog, a region where certainty fades gradually, where sharp distinctions soften, where measurement becomes less about pinning things down and more about describing tendencies. Physicists sometimes describe this regime as space-time foam, a picture where tiny regions of space constantly fluctuate, bubble, and reconnect. Not violently, but incessantly. At this scale, space-time is no longer something you can step on. It is something that seethes, yet even this foam is governed by rules. It is not randomness without structure. It is fluctuation constrained by fundamental constants. Even at the Planck threshold, the universe remains lawful. What changes is not the presence of law, but the kind of law. Classical geometry gives way to quantum geometry. Definite distances give way to distributions. Sharp trajectories give way to probabilistic paths. The universe does not dissolve, it transforms. This transformation has profound implications for how we think about the origin of everything. The early universe existed at energies near or above the Planck threshold. In those first instants, space-time itself was likely subject to quantum uncertainty. The smooth expansion we reconstruct backward from today's cosmos eventually reaches a point where the concept of smoothness fails. This means the beginning of the universe was not simply a smaller, hotter version of what we see now. It was a different regime altogether, one where space and time had not yet settled into their familiar forms. The Planck threshold is therefore not just a limit on measurement, it is a boundary between phases of reality. On one side, the universe behaves like a continuous fabric. On the other, it behaves like a quantum system with no fixed background. Understanding this boundary is one of the deepest goals of modern physics. It is where theories of quantum gravity attempt to operate. It is where new concepts are required, concepts that do not rely on pre-existing space or time. And yet, this boundary remains unreachable by experiment. To reach Planck energy directly would require more energy than all our technology could ever provide. Not because we lack imagination, but because the energy required is immense beyond comprehension. Even the most powerful particle accelerators fall short by many orders of magnitude. This inaccessibility is not a failure. It is another sign of balance. The universe does not allow its deepest structure to be prodded casually. It reveals itself only indirectly, through consistency, through inference, through the quiet alignment of theories that agree up to a point and then fall silent together. As you rest now, consider how far removed your experience is from this threshold. The distances around you are stable. The passage of time feels continuous. Space feels solid enough to support thought, memory, and rest. This stability is not trivial. It is the result of the universe cooling, expanding, and settling far below the Planck threshold. It is what makes calm possible at all. The Planck energy threshold reminds us that reality has layers. that the calm surface we inhabit is underwritten by deeper regimes where familiar concepts no longer apply, and that those regimes are not hostile, just different. They exist quietly beneath everything, not demanding attention, not interfering with daily life. And as we continue this journey, another question gently forms. If the Planck threshold marks the point where space-time loses smoothness, then what exactly does space-time become beyond it? That is where we drift next, into the restless texture beneath reality's calm surface. Part 8. Why space stops being smooth. We often imagine space as a calm, continuous expanse, but at extreme energies, that calm dissolves. Theoretical physics predicts that space-time becomes grainy, turbulent, and restless. Tiny regions bubble in and out of existence. Geometry fluctuates. The universe behaves less like a fabric and more like a stormy sea at microscopic scales. This idea challenges one of our deepest intuitions. From the moment we learn geometry, space is presented as something reliable, a grid, a backdrop, a place where distances can be measured and directions can be trusted. Even when we learn that space can curve under gravity, we still imagine that curve as smooth, like a gently bent surface. For most of the universe, that picture works beautifully. Planets trace graceful paths, light follows predictable arcs, distances can be compared and agreed upon. Space, though dynamic, behaves like something continuous and well-behaved. But this smoothness is not guaranteed at all scales. It is an emergent property. At low energies, space-time averages out its irregularities. Tiny fluctuations cancel one another. Geometry settles into something calm and predictable. This is why classical physics works so well for everyday life and even for much of astronomy. But as we push toward extreme energies and tiny distances, the averaging fails. The calm surface gives way to texture. The reason for this lies in quantum mechanics. At very small scales, uncertainty is unavoidable. Fields fluctuate, energy appears and disappears. Even what we call empty space is not empty. It is alive with transient activity, a restless background of potential. At ordinary scales, this activity is invisible. Its effects cancel out before they can accumulate. But when we zoom in far enough, the fluctuations no longer blur together. They stand out. Now, introduce gravity into this picture. Gravity responds to energy. Even fleeting fluctuations carry energy and therefore gravity. At low energies, their gravitational influence is negligible. At extreme energies, it is not. This creates a feedback loop. Quantum fluctuations distort spacetime. Distorted spacetime changes how fluctuations behave. Each influences the other, amplifying instability. The smooth fabric begins to fray. At this point, space is no longer something you can assume to be continuous. It becomes granular, not in the sense of solid grains, but in the sense of ever-shifting patches of geometry. Distances lose precision. 2 points that appear distinct in one moment may blur together in the next. The concept of between becomes unreliable. Physicists describe this regime using metaphors like foam, turbulence, or boiling. Not because space literally behaves like water, but because these images capture the loss of smoothness, the loss of calm continuity. In this regime, space-time does not sit still long enough to be treated as a stable background. It fluctuates on timescales so short and distances so small that no classical measurement can keep up. This is why space stops being smooth, not because it breaks, but because it refuses to settle. Importantly, this restlessness does not extend upward indefinitely. It is confined to extreme scales. Just as the surface of the ocean can be violently turbulent while the depths remain calm, space-time can be chaotic at microscopic scales while appearing smooth at macroscopic ones. This layered behavior is essential. If space-time were turbulent at all scales, nothing stable could exist. No atoms, no stars, no memories. The fact that space smooths out as you zoom out is what allows the universe to be habitable. Smoothness, then, is not fundamental. It is a large-scale illusion born from averaging. At the smallest scales, space is not a stage, it is a process. This realization forces a quiet shift in perspective. We often think of space as something that things are in, But at extreme energies, it becomes something that things are made of, something that participates, something that fluctuates. Geometry becomes dynamic in a new way. In classical general relativity, geometry is dynamic because it responds to mass and energy. In quantum gravity regimes, geometry is dynamic because it fluctuates on its own, even in the absence of classical matter. This is a subtle but profound difference. It suggests that space itself has degrees of freedom, that it can vibrate, twist, and rearrange independent of the objects within it. At these scales, talking about where something happens becomes problematic. If the geometry itself is uncertain, then location is no longer a fixed label. It becomes a probability distribution. Similarly, talking about when something happens becomes ambiguous. Time, woven into space-time, shares its instability. Events do not line up neatly along a single timeline. This does not mean causality vanishes. It means causality becomes local and probabilistic rather than global and rigid. These ideas are difficult to visualize, and that is okay. They are not meant to be intuitive. They are meant to be consistent. The universe does not prioritize our comfort. It prioritizes coherence. One way to think about this is to imagine zooming in on a photograph. From far away, the image looks smooth. Colors blend seamlessly. Shapes are clear. But as you zoom in far enough, individual pixels appear. The smooth gradients break into discrete points. The image is still real, but its nature changes. Space-time may behave in a similar way. At large scales, it appears smooth. At small scales, its underlying structure becomes visible, not as solid pixels, but as fluctuating elements governed by quantum rules. This analogy has limits, but it captures the essence of the transition. Smoothness is not absolute. It depends on scale. What makes space-time special is that its pixels, if they exist, are not fixed. They flicker, they rearrange, they are probabilistic. This flickering is not something we can observe directly. Any attempt to probe it with sufficient resolution introduces enough energy to distort it further, creating horizons and blocking information. The very act of looking intensifies the turbulence. This is why space stops being smooth, precisely where observation becomes impossible. The breakdown of smoothness and the emergence of horizons are not separate phenomena. They are two sides of the same boundary. One describes what happens to geometry, the other describes what happens to information. Together, they mark the edge of classical understanding. And yet, beyond this edge, physics does not end. It continues in a different language, a language we are still learning to speak. Theories of quantum gravity attempt to describe this restless spacetime. Some suggest that space is built from discrete loops. Others propose that it emerges from more fundamental relationships, with geometry arising from patterns of entanglement. These ideas differ, but they agree on one thing. Smooth space is not fundamental. It is a consequence of calm. As the universe cooled from its earliest moments, energy densities dropped, fluctuations softened, geometry settled, space became smooth enough for structure to form, galaxies condensed, stars ignited, planets coalesced, life emerged. The calm you experience now is the universe far below the energies where space loses its smoothness. That calm is precious. It allows thought to flow without interruption. It allows memory to persist. It allows rest. As you lie quietly now, imagine the layers beneath that calm, beneath the steady room around you, beneath the planet carrying you through space, beneath even the atoms of your body. At unimaginably small scales, space-time may be churning, restless, alive with fluctuation, not threatening, not chaotic in the everyday sense, simply active. And that activity is contained, isolated, prevented from spilling upward into the world you inhabit. This containment is what allows smoothness to exist at all. And as we continue this journey, one final image begins to form. If space at the smallest scales is not smooth but foamy, restless, and fluctuating, then what does that foam actually look like? That question leads us deeper still into the strange texture physicists have given a name to, and which waits quietly beneath everything. Part 9. The foam beneath reality. Physicist John Wheeler gave this restless structure a name: quantum foam. At Planck Energy, space is no longer empty or stable. It froths with transient distortions, microscopic black holes, and fleeting geometries. This is not metaphor. It is a mathematical prediction born from the deepest equations we have, describing a universe that refuses stillness at its smallest scale. To appreciate what quantum foam means, it helps to release the idea that empty space is truly empty. Even far from stars, planets, or particles, space is not a void. Quantum physics tells us that every field fluctuates, energy briefly appears and vanishes. Pairs of particles flicker into existence and dissolve again, too quickly to be directly observed, yet real enough to leave measurable traces. At ordinary scales, these fluctuations average out. Their effects cancel one another, leaving behind the calm, stable space we experience. But as you move closer to the Planck scale, that averaging no longer works. The fluctuations do not have room to smooth themselves away. They pile up. They interfere. They reshape the geometry they inhabit. This is where Wheeler's insight becomes essential. If energy fluctuates, and energy creates gravity, then gravity must fluctuate as well. And if gravity fluctuates, then space-time itself cannot remain fixed. It must ripple, warp, and twist in response. Quantum foam is the name for this restless state of space-time. In this regime, space is not a continuous backdrop. It is an active participant. Tiny regions curve sharply, collapse inward, and release again. Microscopic black holes may form briefly, not as permanent objects, but as momentary geometric events. Wormhole-like distortions may open and close, not as tunnels for travel, but as fleeting rearrangements of connectivity. These features are not stable enough to be visited. They are not places you could go. They are patterns of fluctuation, existing only for unimaginably short moments and over unimaginably small distances. Yet their existence follows inevitably from combining quantum mechanics with general relativity. This inevitability is what makes quantum foam so compelling. It is not a speculative embellishment, it is the natural outcome of taking our best theories seriously at extreme scales. What makes it difficult to grasp is that foam suggests a universe that is fundamentally dynamic even in its emptiest regions. Stillness, in this view, is an illusion created by scale. When you zoom out far enough, the turbulence disappears. When you zoom in far enough, it becomes unavoidable. Imagine standing on the shore of a calm lake. From a distance, the surface looks smooth and reflective, but up close, tiny ripples dance across it. Go closer still, and molecular motion dominates. Zoom all the way down, and the idea of a smooth surface vanishes entirely. Quantum foam suggests that space-time behaves in a similar way. At human scales, space is smooth. At atomic scales, it remains smooth enough to support stable structures. But at Planck scales, it dissolves into restless activity. Importantly, this foam is not chaotic in the everyday sense. It is constrained by fundamental constants. Its fluctuations have characteristic sizes and durations. They are not arbitrary. They obey statistical rules. This distinction matters. Chaos implies unpredictability without structure. Quantum foam implies unpredictability within structure. The universe is not breaking down. It is operating in a regime where probability replaces certainty. In this foamy regime, familiar concepts lose their footing. Distance becomes fuzzy. 2 points that seem separate may be indistinguishable within quantum uncertainty. The idea of a straight line loses meaning when the geometry itself fluctuates faster than anything can traverse it. Time, too, becomes uncertain. Events cannot be cleanly ordered when space-time itself is in flux. The sequence of cause and effect becomes local and contextual rather than global and absolute. This does not mean causality disappears. It means it no longer applies universally. Causality survives as a local rule, valid within small regions and short durations. Beyond that, it dissolves into probability. This idea unsettles us because we are creatures of narrative. We rely on before and after, on continuity, on stable relationships between events. Quantum foam challenges these assumptions at the deepest level. And yet, The challenge is contained. Quantum foam does not leak upward into everyday experience. It does not disrupt atoms, molecules, or biological processes. Its effects are confined to scales far beyond direct reach. This confinement is crucial. If quantum foam extended to larger scales, the universe would be uninhabitable. Nothing could remain stable long enough to exist. The fact that foam remains microscopic is what allows macroscopic calm. This again points to balance. The universe permits extreme behavior only where it cannot propagate outward. Horizons, uncertainty, and fluctuation work together to isolate the foam, keeping it from infecting larger scales. This isolation is why we can talk about space at all. The space you experience is not fundamental. It is an emergent average, a calm surface floating atop a restless sea. Quantum foam is what that sea looks like beneath the surface. Physicists have explored this idea using different approaches. Some imagine space-time as composed of discrete units that rearrange. Others imagine it as a network of relationships, with geometry emerging from patterns of quantum entanglement. Still others explore mathematical structures where space-time itself is not primary, but derived. Despite their differences, these approaches converge on a shared insight. Space-time is not a fixed thing. It is a dynamic process. The foam is the process at its most intense. It is worth noting that quantum foam is not directly observable. Any attempt to observe it would require energies that create horizons, sealing the region off from view. This makes foam both fundamental and hidden. It influences the universe's structure without ever being seen. This hidden influence may explain why space-time behaves the way it does at larger scales. The smoothness of space may be a statistical result of averaging over foam. The dimensionality of space may emerge from the way fluctuations connect and cancel. Even the arrow of time may trace back to asymmetries in these fundamental processes. These ideas remain speculative, but they are grounded in careful reasoning. They arise not from imagination alone, but from consistency. The foam beneath reality is not an artistic flourish. It is a consequence of refusing to ignore either quantum mechanics or gravity. As you rest now, consider how strange and quiet this is. Beneath the floor supporting you, beneath the planet beneath you, beneath the atoms that compose your body, beneath even the space between those atoms, there may be no emptiness at all. Instead, there may be a ceaseless dance of creation and collapse, not loud, not violent, just persistent. And yet, you feel none of it. That is the miracle of scale. The universe is vast enough to contain extremes without letting them dominate. It is layered enough to be both restless and calm at the same time. Quantum foam is the restless layer, the foundation that never settles, yet supports everything above it. And as we continue this journey, another question begins to surface gently from the foam itself. If space-time is so restless at the smallest scales, and if energy beyond a certain point seals information away, then why can no machine, no matter how large, ever reach this regime directly? That question brings us next to the limits not of theory, but of possibility itself. Part 10. Why no machine can ever reach this energy. Even with all human ingenuity combined, Planck energy remains unreachable. Not because we lack materials or funding, but because the energy required exceeds what entire stars produce. Even a particle accelerator the size of a galaxy would fall short. This limit is not technological, it is cosmic. A built-in safety boundary that shields the universe's deepest structure from direct inspection. At first, this claim feels almost pessimistic. Human history is full of barriers that once seemed absolute. We could not fly. We could not leave Earth. We could not split the atom. Each limit eventually fell, not through brute force alone, but through insight. So it is natural to wonder whether Planck energy is simply another challenge waiting for the right idea. Physics gives a gentler but firmer answer. This boundary is different. To understand why, consider what it actually means to reach a certain energy in an experiment. It is not enough to possess a large amount of energy in total. The energy must be delivered to a single interaction, focused into a tiny region of space and time. Only then does it probe small distances. This is why particle accelerators are built the way they are. They do not store energy like a battery. They concentrate it into individual particles, accelerating them to extreme speeds so that when they collide, their energy is available all at once in one place. As we have pushed these machines to higher and higher energies, we have encountered familiar engineering challenges: stronger magnets, larger rings, more precise control. Each generation improves on the last. But Planck Energy does not merely require a bigger ring, it requires a fundamentally different universe. The energy associated with the Planck scale is so enormous that when translated into everyday terms, it defies intuition. It is the kind of energy you would get by accelerating a single particle to a speed so close to the speed of light that the remaining difference becomes meaningless. And even then, the required energy is immense. To reach it, you would need to pour energy into a single particle far beyond what stars routinely produce. This is not a matter of efficiency. It is a matter of scale. Stars generate enormous power, but they distribute it across vast volumes and long times. They shine by spreading energy out, not by focusing it. Planck scale probing demands the opposite: extreme concentration. Even if you imagined capturing the total output of a star and channeling it into a single particle, you would face another obstacle: gravity. As energy concentration increases, gravitational effects grow. The apparatus itself would begin to curve spacetime. The energy would collapse inward before it could be used. Horizons would form. Information would be sealed away. In other words, the attempt would sabotage itself. This is why even hypothetical machines of absurd size fail. A particle accelerator the size of the Earth would not be enough. One the size of the solar system would not suffice. Even one spanning the galaxy would still fall short. Not because it could not accelerate particles, but because the act of concentrating enough energy would trigger gravitational collapse long before Planck energy was reached. The universe does not allow arbitrary concentration. This is the crucial insight. Technological limits can be overcome by better materials, clever designs, or new principles. Cosmic limits arise from the structure of reality itself. They do not yield to ingenuity because they are not obstacles placed in our way. They are consequences of consistency. If it were possible to reach Planck energy directly, space-time itself would lose stability on macroscopic scales. The universe would permit its deepest layers to influence higher ones uncontrollably. This would undermine the very separation of scales that allows complexity to exist. So instead, the universe enforces a separation. Extreme energies are allowed only in extreme conditions, and even then, they are isolated. Black holes contain them. The early universe contained them, but they do not propagate outward freely. This isolation is not cruel. It is protective. It ensures that the calm, structured world you inhabit is not constantly disrupted by the most violent processes possible. It allows stars to burn steadily rather than collapsing instantly. It allows space to remain smooth enough for motion and memory. From this perspective, the impossibility of reaching Planck energy is not a failure of ambition. It is a feature of stability. There is also a subtler reason machines cannot reach this regime, one that has nothing to do with size or power. Information itself becomes inaccessible. As we have seen, beyond a certain energy density, horizons form. These horizons prevent information from escaping. Even if a machine could create Planck scale conditions locally, it could never retrieve data from them. The results would be causally disconnected from the rest of the universe. An experiment that cannot return results is not an experiment at all. This means that even in principle, direct experimental access to Planck scale physics is impossible. The universe allows such conditions to exist, but not to be interrogated from the outside. This forces physics into a quieter mode of inquiry. Instead of direct probing, we rely on indirect evidence. We study the large-scale structure of the universe. We examine the behavior of black holes. We analyze subtle patterns in cosmic radiation. We look for consistency across theories that must agree below the threshold and remain silent above it. This is not a weakness. It is a different way of knowing. Much of what we know already comes from inference rather than direct observation. No one has ever seen the interior of a star's core, yet we understand nuclear fusion. No one has ever watched space-time curve, yet we measure its effects precisely. Planck-scale physics may belong permanently to this inferred category, known not by seeing, but by necessity. This changes the tone of inquiry. Instead of building ever larger machines, we refine our understanding of principles. We ask what must be true for the universe to behave as it does at accessible scales. We look for theories that naturally incorporate Planck-scale limits without contradiction. In this sense, the unreachable energy becomes a guide rather than a frustration. It tells us where our descriptions must change. It tells us where new ideas are required. It tells us that reality has a structure that resists infinite reduction. As you rest now, it may be comforting to realize that there are places the universe does not expect us to go. Not because we are unworthy, but because going there would unravel the conditions that allow us to exist at all. The deepest layers of reality are not hidden behind complexity alone. They are hidden behind balance. The universe permits exploration, but only within bounds that preserve coherence. It invites curiosity, but not domination. It reveals patterns, but not infinite detail. This restraint is what allows wonder to coexist with stability. The fact that no machine can ever reach Planck energy does not mean those depths are meaningless. It means they are foundational. They support everything above them without ever needing to be exposed. They are like the bedrock beneath an ocean, never seen directly, yet shaping every current, every wave, every surface reflection. And as we continue this journey, one more thought begins to emerge gently from this realization. If the universe enforces such strict limits to protect its deepest structure, then perhaps these limits are not obstacles at all, but expressions of care. That idea carries us next into a quieter reflection, how the universe, in drawing these boundaries, protects itself and us from its own extremes. Part 11. The universe's quiet act of self-protection. Planck energy acts like a lock on reality's most sensitive mechanisms. As you push closer, the universe responds by hiding information behind horizons. It doesn't break, it protects itself. This suggests that the universe is not infinitely divisible, but carefully structured, with boundaries that preserve consistency and prevent paradox. This idea can feel almost personal, as though the universe is actively guarding its secrets. But the protection is not intentional in the human sense, it is structural. The laws of physics are arranged in such a way that extreme conditions do not propagate freely. They are contained, isolated, quietly managed. To see why this matters, imagine a universe without such protection, a universe where energy could be concentrated without limit, where geometry could be dissected indefinitely, where information could be extracted from arbitrarily small scales without consequence. In such a universe, stability would be impossible. Tiny fluctuations would cascade upward, local extremes would leak outward. Nothing could remain calm long enough to exist. Atoms would not hold together. Stars would not burn steadily. Time itself would fracture into contradictions. The universe we inhabit avoids this fate not by forbidding extremes, but by isolating them. Horizons are the key. Whenever energy density grows too large, space-time responds by creating regions that are causally sealed. Information inside cannot influence the outside. This prevents runaway effects. It ensures that extreme behavior remains local, unable to unravel the larger structure of reality. This is what self-protection looks like in physics. Not walls, not barriers you can touch, but limits on communication, limits on influence, limits on what can affect what. At Planck Energies, this protection becomes absolute. Any attempt to probe deeper creates conditions that block the return of information. The universe does not allow its foundational layer to be pulled apart and broadcast outward. This is not a failure of measurement. It is a requirement for coherence. Physics depends on consistency. Causes must precede effects. Predictions must not contradict one another. Conservation laws must hold. If space-time could be arbitrarily subdivided and interrogated without restriction, these principles would collapse under their own weight. By enforcing a minimum scale of meaningful measurement, the universe preserves logical structure. This preservation is subtle but profound. It means that reality is not a bottomless stack of layers, each revealing more detail than the last. Instead, it is more like a carefully balanced system, where detail gives way to principle. Where questions about what is smaller eventually turn into questions about what is allowed. In this sense, Planck energy is not just a limit, it is a safeguard. It ensures that quantum uncertainty and gravitational curvature do not spiral into contradiction. It ensures that the laws of physics remain compatible with one another, even when pushed to their extremes. This compatibility is what allows us to use mathematics at all. Equations work because the universe does not allow pathological behavior to dominate. Singularities are hidden, divergences are sealed away, infinities are avoided or isolated. Without this self-protection, physics would be impossible. There is also a quieter implication here, one that touches on the nature of explanation itself. When we ask questions about the deepest structure of reality, we often assume that answers must come in the form of finer detail, smaller pieces, more resolution. But the universe suggests a different approach. At the deepest level, explanation may not come from subdivision, but from principle. The Planck boundary redirects inquiry away from what lies beneath and toward what must be true. It invites us to seek consistency rather than detail, coherence rather than granularity. This is a different kind of knowledge. It is the kind that does not rely on direct observation, but on necessity, on asking what conditions must hold for the universe to behave as it does at accessible scales. In this way, the universe's self-protection does not block understanding. It reshapes it. It teaches us humility. There are places where forceful curiosity becomes destructive, not because curiosity is wrong, but because the method is mismatched to the structure of reality. At Planck energies, gentleness is not an option. Any probe becomes overwhelming, so the universe refuses to cooperate. Instead, it invites patience. We are allowed to infer, to reason, to build frameworks that respect boundaries rather than violate them. This is why modern theoretical physics spends so much effort on internal consistency, on symmetry, on principles that hold across scales. These are the only tools that can cross the Planck boundary indirectly. The universe's quiet act of self-protection is also what allows time to have meaning. If information could escape arbitrarily from extreme regions, causality would be compromised. Effects could appear without causes. Time ordering would fail. By sealing off extremes, the universe preserves a global arrow of time for the rest of reality. This arrow is what allows memory. It is what allows experience. It is what allows you to remember lying here now, listening, resting. The calm continuity of time you feel is not guaranteed by default. It is maintained by boundaries you never see. This makes the universe feel less like a machine and more like a system of balances, where extremes exist but are contained, where violence is possible but isolated, where calm emerges because chaos is kept local. As you breathe quietly, consider how many layers of protection separate your experience from the most extreme processes in existence. Between you and Planck scale turbulence lie atoms, molecules, biological systems, planetary gravity, stellar structure, galactic organization, and cosmic expansion. Each layer buffers the next. The universe is not fragile, it is robust because it is layered. Planck energy marks the deepest of these layers, the place where the buffering stops, the point beyond which reality cannot be subdivided without losing coherence. This is why the universe does not shatter when pushed. It redirects, it hides, it seals. And this sealing is not arbitrary, it is precise. It occurs exactly where it must to preserve consistency between quantum mechanics and gravity. There is a quiet elegance in that precision. The universe does not rely on ad hoc fixes. It does not patch contradictions after they appear. It prevents them from arising by structuring itself with care. In doing so, it protects not just its deepest mechanisms, but everything that depends on them. Stars can burn steadily because their cores are protected from runaway collapse. Galaxies can persist because their extreme centers are sealed. Space can remain smooth at large scales because its turbulence is confined to the smallest ones. Even thought itself depends on this protection, on the fact that energy does not spontaneously concentrate without bound, on the fact that information does not erupt uncontrollably from every scale. As this part of our journey comes to rest, one more question emerges, gentle and patient. If the universe protects itself by hiding its deepest structure, then how can we ever hope to understand it at all? The answer lies not in force, but in reflection. Not in breaking boundaries, but in listening to the patterns that remain. That reflection carries us forward toward the early universe, where these protected mechanisms briefly revealed their influence before retreating behind the veil of expansion. Part 12. What the Big Bang shared with Planck Energy. The early universe passed through energies near the Planck scale. In those first instants, space and time were not yet settled into their familiar forms. Studying Planck energy is not just about extremes, it is about origins. It connects the smallest scales imaginable to the birth of everything that exists. To imagine the beginning of the universe, it helps to let go of images of explosions or expanding fireballs. Those pictures are useful metaphors, but they can distract from what physics actually describes. The Big Bang was not an event that happened in space. It was an event from which space itself emerged. And in its earliest moments, the universe was governed by conditions so extreme that our usual ideas of distance, duration, and structure did not yet apply. In those first fractions of a second, energy densities were unimaginably high, not spread across galaxies or stars, but compressed into the entire cosmos itself. The universe was small, hot, and intensely energetic, and at that scale, the same principles we have been exploring come into play. Quantum uncertainty was unavoidable. Gravity was overwhelming. Space-time itself was subject to fluctuation. This is what links the Big Bang to Planck energy. The Planck scale is not just a theoretical boundary we approach from the present, it is a regime the universe once inhabited. Before galaxies, before atoms, before even particles as we know them, reality existed in a state where the distinction between energy, space, and time had not yet crystallized. At that moment, the universe was not smooth, it was not calm, it was not structured, it was closer to the restless foam we've been describing, but on a cosmic scale. And yet, from that restlessness, order emerged. As the universe expanded, energy spread out, density dropped, gravity softened, quantum fluctuations began to average away. Space-time cooled into a geometry that could support stable relationships. Distances became meaningful, time acquired direction, causality settled into place. This transition is one of the most important processes in all of physics. It marks the moment when the universe became describable in the terms we use today. Before this transition, our equations fail, not because the universe was chaotic, but because the concepts they rely on did not yet exist. You cannot describe smooth expansion if smoothness itself has not formed. You cannot define time intervals if time is fluctuating. You cannot measure distance if space has no stable geometry. The Big Bang, then, was not just a beginning. It was a phase change. Just as water transitions from vapor to liquid, the universe transitioned from a Planck scale regime into a classical spacetime. This transition did not happen instantly. It unfolded as energy density fell below critical thresholds. Each threshold unlocked new possibilities. As gravity weakened relative to other forces, space became less turbulent. As quantum fluctuations lost dominance, geometry stabilized. As temperatures dropped, particles could exist without immediately annihilating one another. Matter gained identity, forces separated, symmetry broke. These processes are still being studied, but the broad picture is clear. The universe we know emerged gradually from Planck scale conditions. This means that Planck energy is written into everything. It shaped the initial conditions from which all structure grew. It influenced the distribution of matter. It set the stage for cosmic inflation, the rapid expansion that smoothed out the universe on large scales, while preserving tiny fluctuations that later became galaxies. Those fluctuations are still visible today. When we observe the cosmic microwave background, the faint afterglow of the early universe, we are seeing a snapshot of reality as it cooled enough for light to travel freely. The tiny temperature variations in that background encode information about conditions that trace back toward Planck scale physics. In this way, the universe carries memory, not memory in the human sense, but memory in structure. Patterns imprinted early persist, amplified by expansion and gravity. The largest structures in the cosmos may ultimately owe their existence to quantum fluctuations that occurred when the universe was smaller than an atom. This connection between the smallest and largest scales is one of the most beautiful features of modern cosmology. It tells us that extremes are not isolated curiosities. They are formative. The Planck regime did not remain hidden forever. It shaped everything before retreating behind the veil of expansion. It left fingerprints that we can still study, even if we cannot return to that regime directly. This is how the universe allows us to learn without reopening old wounds. It reveals its origins indirectly through consequences rather than access. There's also a deeper philosophical implication here. If space and time themselves emerged from Planck scale conditions, then they are not fundamental ingredients of reality. They are outcomes, products of a deeper process. This challenges the way we think about existence itself. It suggests that asking what happened before the Big Bang may be a meaningless question, not because nothing existed, but because before may not have existed as a concept. Time itself may have emerged along with space. In that case, the Planck regime is not just a boundary in energy. It is a boundary in language. Beyond it, words like before, after, here, and there lose their anchors. This does not mean the early universe was unknowable. It means it must be approached differently, through mathematics, through consistency, through careful reasoning about what must have been true for the universe to become what it is. This approach has already yielded profound insights. It has told us that the universe is remarkably flat on large scales, that it expanded rapidly early on, that tiny fluctuations grew into vast cosmic structures, that the laws of physics were forged in conditions far removed from anything we experience now. All of this traces back, directly or indirectly, to Planck scale physics. And yet, the universe has moved far away from that state. As it expanded, it diluted its own extremes. It created room. It allowed calm to emerge. The violent intimacy of Planck scale reality gave way to the spaciousness we inhabit now. This distance is what allows reflection. As you lie quietly now, the universe around you is ancient and cool, its energy spread thinly across immense volumes. The violent conditions of its birth are not gone, but they are deeply buried beneath layers of expansion and time. This distance is not accidental. It is what allows stars to burn slowly instead of exploding instantly. It is what allows planets to orbit stably. It is what allows thought to persist longer than a heartbeat. The Big Bang shared something profound with Planck energy: intensity, density, a closeness of everything to everything else. But the universe did not remain there. It moved away deliberately, according to its laws, into a regime where structure and calm could exist. Understanding Planck energy is therefore not about returning to the beginning. It is about understanding the conditions that made departure possible, the rules that allowed the universe to evolve from turbulence into tranquility. As this part of our journey comes to rest, another quiet question rises. If the universe once existed in a state where time itself was unsettled, then what does that tell us about time today? That question leads us next into one of the most delicate ideas of all: whether time, like space, loses its meaning at extreme energy, and what remains when it does. Part 13. Why time loses its meaning at extreme energy. At everyday scales, time flows smoothly. Seconds follow seconds. But at Planck energy, time itself becomes uncertain. The equations no longer allow a single direction or rhythm. Cause and effect blur. The universe stops offering a clear before and after. Time becomes a local, fragile concept rather than a universal rule. In daily life, time feels like the most reliable feature of reality. You can close your eyes, take a breath, and trust that moments will continue arriving in the same order they always have. Morning follows night. One thought follows another. Even when everything else changes, time seems to move forward with quiet certainty. Physics, however, tells us that this certainty is conditional. Time behaves smoothly only because the universe is calm at the scales we inhabit. Energy is spread out, space is stable, motion is gentle enough that time can be treated as a steady background. Under these conditions, clocks agree with one another, events can be ordered. Cause leads to effect in a way that feels absolute. But this order is not guaranteed everywhere. As energy density increases, time begins to behave differently. We already know this from relativity. Clocks run more slowly in strong gravitational fields. Time passes differently for objects moving at different speeds. These effects are small in daily life, but they are real and measurable. Even now, time is not universal. What changes at extreme energy is not just the rate at which time flows, but the very idea of time as a single, shared dimension. At the Planck scale, the assumptions that make time meaningful begin to fail. To define time, you need a stable sequence of events. You need a way to say that one event happens before another. You need a geometry that allows you to compare durations across space. All of these depend on space-time being smooth enough to support consistent clocks. At extreme energies, space-time is not smooth. As we've explored, quantum fluctuations dominate. Geometry itself becomes uncertain, space flickers, distances blur, and because time is woven inseparably into space, it inherits this instability. In this regime, asking when something happens becomes ambiguous. Quantum mechanics already challenges the classical notion of time. In quantum systems, events do not always occur at sharply defined moments. Particles exist in superpositions. Processes unfold probabilistically. The idea of a precise timeline gives way to a range of possibilities. Normally, these effects average out. Time emerges as a useful approximation. But when energy densities rise toward the Planck scale, that averaging no longer works. Fluctuations in energy imply fluctuations in gravity. Fluctuations in gravity imply fluctuations in the rate at which time flows. There is no longer a single clock that everyone can agree on. Time becomes local. In one tiny region, processes may unfold quickly. In a neighboring region, they may unfold more slowly. The difference is not a matter of perspective. It is built into the geometry itself. This destroys the notion of a global now. At everyday scales, we can imagine slicing the universe into moments, each representing the present. At extreme energies, such slices cannot be defined consistently. Different regions disagree on what counts as simultaneous. Worse, the disagreement fluctuates over time. There is no stable present to slice. Cause and effect, which rely on temporal order, become subtle. It is no longer meaningful to say that one event universally causes another. Causality becomes local and conditional, valid only within limited regions where space-time behaves coherently. This does not mean causality disappears entirely. It means it loses its global authority. In a calm universe, causality is like a river flowing steadily downhill. At extreme energies, it becomes more like eddies in a turbulent sea. Direction exists locally, but there is no single downstream. This is deeply counterintuitive, and that discomfort is a signal that we are leaving the domain our minds evolved to navigate. Time, as we experience it, is an emergent phenomenon. It arises when conditions are right. Those conditions include low energy density, smooth spacetime, and weak gravitational gradients. Under those circumstances, time behaves like a reliable dimension. It can be measured, it can be shared, it can be trusted. At the Planck scale, those conditions vanish. The universe does not offer a master clock. It offers only local rhythms, each shaped by fluctuating geometry. The idea of a universal timeline dissolves. This has profound implications for how we think about beginnings. If time loses its meaning at extreme energy, then asking what happened before the Big Bang may not make sense, not because nothing existed, but because before requires a time framework that did not yet exist. The early universe may not have unfolded in time as we understand it. Instead, time may have emerged as the universe cooled and expanded, stabilizing space-time enough to support consistent temporal order. In this view, time is not a fundamental ingredient of reality. It is a product. It is something the universe does, not something it has. This perspective helps resolve some of the deepest puzzles in cosmology. It explains why the beginning of the universe does not require a cause in the usual sense. Causation itself may only apply after time emerges. It also explains why physics struggles to describe the Planck regime. Our equations are built on time. They assume it exists. When time itself becomes uncertain, the language of those equations loses footing. Some approaches to quantum gravity attempt to describe reality without time at all, treating it as an emergent parameter that appears only in certain limits. In these models, the universe exists as a network of relationships rather than a sequence of moments. Change still occurs, but not in time. Instead, time emerges from change. This is difficult to picture, and it may always remain so, but it aligns with the idea that time is fragile, dependent, conditional. At extreme energy, the universe does not promise continuity. What is striking is that this fragility does not threaten daily life. The conditions that dissolve time are far removed from the ones we inhabit. Energy densities here are low. Space-time is smooth. Time behaves kindly. The universe allows time to exist where it is useful. This usefulness is not trivial. Time enables memory. It allows learning. It permits rest. Without a stable sense of before and after, nothing could accumulate meaning. The fact that time emerges and persists at the scales we inhabit is one of the quiet miracles of the cosmos. As you lie here now, time feels slow and steady. Each breath arrives after the last. Each thought fades into the next. This continuity is not guaranteed everywhere, but it is guaranteed here. And that guarantee exists because the universe has moved far from the extreme energies where time dissolves. This distance is a form of safety. The violent, timeless regime of the early universe has retreated behind expansion and cooling. It no longer intrudes. It has done its work and stepped aside, allowing time to take shape. Understanding that time can lose its meaning does not diminish its value. It deepens it. It tells us that time is not an infinite backdrop stretching unchanged across all of reality. It is a local achievement, a structure that emerges when conditions allow. This makes each moment feel quieter, more delicate. Time is not guaranteed forever. It is sustained. And like all sustained things, it depends on balance. As this part of our journey settles, one final question gently forms. If time and space both lose their familiar meanings at extreme energy, then what remains fundamental when both dissolve? That question carries us forward into the search for theories that attempt to describe reality without assuming space or time at all, and into the recognition that our deepest understanding may lie not in measurement, but in pattern. Part 14. What future theories are still searching for physicists? Believe that beyond Planck energy lies a deeper theory, one that unites gravity and quantum mechanics into a single language. String theory, loop quantum gravity, and other approaches are attempts to describe what exists beyond this boundary. Each is a quiet admission that our current understanding ends here. This admission is not a failure. It is a marker of honesty. For all the success physics has had in describing the universe, there is a place where our most trusted ideas stop agreeing. Beyond that place, we do not yet have a complete map. What we have instead are directions, hints, and carefully constructed questions. Future theories are not searching for more detail in the usual sense. They are not trying to zoom in further with sharper tools. They are searching for a new way to describe reality that does not rely on assumptions that break down at extreme energy. At the Planck scale, space and time themselves become unreliable. Any theory that assumes a smooth space-time background is already standing on ground that no longer exists. So the search is not just for new equations, but for a new foundation. One of the central challenges is this: how do you describe gravity in a quantum world? Quantum mechanics treats interactions as exchanges between discrete entities governed by probabilities and uncertainty. Gravity, as we currently understand it, treats space-time as a continuous geometry that responds smoothly to energy and mass. These pictures are deeply different. Trying to force one into the other creates contradictions. Future theories aim to resolve this not by choosing one picture over the other, but by finding a deeper framework from which both emerge. In this sense, gravity and quantum mechanics may not be fundamental rivals. They may be surface expressions of something more basic. This idea has guided decades of research. Some approaches imagine that the fundamental building blocks of reality are not particles at all, but extended objects whose vibrations give rise to everything we observe. Others imagine that space itself is woven from discrete loops or networks, with geometry emerging from how these elements connect. Despite their differences, these approaches share a common theme. They attempt to remove space-time from the list of assumptions. Instead of starting with space and time and placing physics inside them, they attempt to derive space and time as outcomes, as patterns that emerge when deeper rules operate at lower energy. This shift is subtle but profound. It means that what we experience as space may be more like a shadow than a substance, a large-scale appearance created by underlying relationships, and time may be less like a river flowing on its own, and more like a measure of change within those relationships. Future theories are searching for these relationships. They ask questions like, what does it mean for two things to be near each other if space is not fundamental? What does it mean for one event to come before another if time is emergent? How do cause and effect arise without a background clock? These questions sound abstract, but they are motivated by necessity. At Planck Energy, the usual answers stop working. The challenge is not only conceptual, but mathematical. Any successful theory must reproduce everything we already know at accessible scales. It must explain why spacetime appears smooth when energy is low, why gravity behaves classically in most situations, why quantum mechanics works so well for particles and fields. In other words, the new theory must contain the old ones as approximations. This requirement is strict. It severely constrains what future theories can look like. Many ideas are ruled out not because they are imaginative, but because they fail to recover known physics in the right limits. This is why progress is slow. Physics advances fastest when experiments can guide theory. At the Planck scale, direct experiments are impossible. So, theory must guide itself, using consistency, symmetry, and mathematical coherence as its compass. This kind of search is quiet. It happens on paper, in thought, in careful argument. There are no dramatic breakthroughs announced overnight. Instead, there are gradual refinements, better questions, deeper connections, occasional unifications of ideas that once seemed unrelated. This slowness can feel frustrating, but it is also a sign of care. The stakes are high. A theory that claims to describe reality beyond space and time must be exceptionally disciplined. What future theories are ultimately searching for is not complexity, but simplicity of a deeper kind. Not fewer equations, but fewer assumptions. They aim to identify principles so fundamental that everything else follows naturally. Principles that do not rely on background structures, but generate them. In this sense, the search resembles earlier moments in physics, when gravity was unified with motion, when electricity and magnetism were revealed as two aspects of one phenomenon, when space and time were unified into space-time. Each unification required letting go of familiar categories and trusting abstraction. The next step may be even more demanding. It may require letting go of space and time themselves as starting points. There is something humbling about this search. It reminds us that our most intuitive concepts are not guaranteed to be fundamental. They are shaped by the scales at which we evolved, by the calm, low-energy environment we inhabit. Reality, at its deepest level, may not resemble our intuitions at all, and yet that reality gives rise to us. This is one of the quiet wonders of physics, that from a foundation so unlike our experience, a universe emerges that can support experience at all. Future theories are trying to explain this emergence. They are trying to answer how something as orderly as spacetime and something as familiar as time's flow can arise from rules that do not include them explicitly. They are also trying to explain why the universe has the constants it does, why the Planck scale sits where it does, why the boundary between regimes is placed just so. These are not idle questions. Small changes in these constants would make the universe unrecognizable. Stars might not form, chemistry might not work, stability might be impossible. Understanding why the universe is structured the way it is may require understanding the Planck regime. And yet, even as physicists search, there is an acceptance that some aspects may remain indirect, that we may never see beyond the boundary. That understanding may always come through inference rather than observation. This acceptance does not diminish the search, it defines it. Science is not only about direct access, it is about building coherent pictures that explain what we can observe and predict what we cannot. Future theories are not promises of total knowledge, they are attempts at deeper coherence. As you rest now, it may be comforting to know that the universe does not require us to fully comprehend its deepest layer for it to function. Stars will continue to shine. Time will continue to flow gently here. Space will remain smooth enough to hold thought and rest. The search beyond Planck energy is not urgent for survival. It is a quiet extension of curiosity. It is the universe thinking about itself, through us. And as this part of our journey settles, one final reflection begins to form. If the universe draws a boundary beyond which our familiar concepts dissolve, and if future theories seek coherence rather than conquest, then perhaps the deepest lesson of Planck energy is not about power, but about restraint. That reflection brings us toward the closing of this journey, where we return from the edges of reality to the calm scale we inhabit, carrying perspective rather than answers. Part 15. Why the universe chooses limits. Instead of infinity, infinity feels intuitive to the human mind, but nature rarely uses it. Instead, the universe prefers thresholds, balances, and boundaries. Planck energy is one of these boundaries, reminding us that reality is not endlessly divisible. It is structured, layered, and finite in its deepest expression. And perhaps in that restraint, the universe remains stable enough to exist at all. From a distance, infinity feels comforting. It suggests endless space to explore, endless time to unfold, endless depth beneath every surface. It feels generous, it feels open, and for much of human history, infinity was the simplest answer to difficult questions. If something could not be explained, we imagined it continuing forever. But physics has taught us something quieter. Nature almost never chooses infinity. Wherever we look closely, we find limits instead. Speeds that cannot be exceeded, temperatures that cannot be surpassed, densities that trigger transformation, scales beyond which familiar concepts dissolve. These limits are not imperfections, they are signatures of structure. The universe does not sprawl without restraint, it organizes itself. Planck energy is one of the clearest examples of this organization. It marks the point where pushing further does not reveal more detail, but instead forces a change in the rules. It tells us that reality is not an infinite staircase of smaller and smaller pieces, but a layered system with transitions between regimes. This preference for limits appears everywhere. Light does not travel infinitely fast. Time does not flow identically everywhere. Energy does not concentrate without consequence. Space does not remain smooth at all scales. Each of these facts replaces an imagined infinity with a boundary, and each boundary preserves coherence. Consider what infinity would mean if it were literal. If energy could be concentrated without limit, gravity would overwhelm everything. If space could be divided endlessly, quantum uncertainty would explode. If time could be reversed or duplicated freely, causality would collapse. Infinity, unrestrained, is unstable. The universe avoids this instability by choosing thresholds. At low energies, classical physics works. At higher energies, quantum effects dominate. At still higher energies, gravity reshapes geometry. And beyond a certain point, the universe closes the door entirely, hiding its deepest layer behind horizons and uncertainty. This layered structure allows different rules to operate where they are appropriate. It prevents conflicts from spreading. It allows complexity to emerge without being torn apart by extremes. In this sense, limits are not constraints. They are permissions. They permit stability. They allow the universe to support stars that burn steadily rather than explode instantly. They allow atoms to exist without collapsing. They allow time to flow in a way that supports memory and experience. They allow you to be here now. Infinity, by contrast, would allow nothing to settle. The idea that reality is finite at its deepest level can feel unsettling at first. We are used to thinking of finiteness as restriction, as something taken away. But in physics, finiteness often provides the opposite. It creates room for structure. A violin string produces music precisely because it has fixed length and tension. An endless string would produce nothing but noise. Boundaries create harmony. The universe, it seems, is tuned. Planck energy is part of that tuning. It is where the universe says gently but firmly, this far and no further. Not because it wants to withhold, but because beyond that point, withholding is the only way to preserve consistency. This suggests a subtle philosophical shift. Perhaps reality is not built from infinite possibility constrained afterward, but from carefully chosen constraints that allow possibility to exist at all. The deepest laws may not describe what can happen, but what must not exceed certain speeds, must not concentrate without bound, must not divide without limit. These must-nots are what give rise to everything else. When physicists talk about the universe being well-behaved, this is what they mean. Not that it is simple, but that it is internally consistent, that its extremes do not leak into its everyday functioning. Planck energy is one of the universe's most important lines of containment. It keeps the most violent, restless behavior confined to scales where it cannot dominate. It ensures that smooth space, gentle time, and stable matter can exist elsewhere. This containment is why the universe feels calm most of the time. As you lie here now, nothing around you hints at infinity. The room has size. Your breath has rhythm. Time has direction. Even the night sky, vast as it feels, has structure and limits. The calm you experience is not an accident. It is the product of boundaries doing their work quietly. This perspective can change how we think about knowledge itself. We often imagine understanding as the removal of all limits, as pushing past every boundary until nothing remains hidden. But the universe suggests a different model. Understanding may come from recognizing where boundaries are essential and why they exist. The Planck boundary does not mark ignorance, it marks design. Not design in a deliberate sense, but design in the sense of necessity. The universe could not be otherwise and still exist, and that realization carries a certain peace. It tells us that we do not live in a fragile reality balanced on the edge of chaos. We live in a reality that actively avoids chaos by structuring itself with care. A reality that allows extremes, but only where they can be isolated. Infinity would dissolve that care. Limits preserve it. As we complete this journey from gentle energy to extreme thresholds, from smooth space-time to restless foam, from flowing time to its dissolution, one quiet truth remains. The universe is not endlessly divisible, but it is endlessly subtle. It does not reveal itself by giving us more and more pieces to examine. It reveals itself by showing us where pieces stop being the right question. At Planck Energy, the question is no longer what is smaller, but what is allowed. And that shift from accumulation to balance is perhaps the most important lesson of all. Because in that balance, the universe remains calm enough to exist, structured enough to endure, and gentle enough to be experienced. And here, far from those extremes, in the quiet scale where limits protect rather than constrain, you can rest. The universe is doing its work. You don't need to push any further. As we return from the deepest edges of energy and scale, it becomes clear that the universe is not defined by how far it can be pushed, but by how carefully it holds itself together. We've drifted through thresholds where light becomes too powerful, where space loses its smoothness, where time itself softens and fades into uncertainty. And yet, through all of it, one quiet pattern remains. The universe does not unravel. It responds, it protects, it balances. Planck energy marks the place where curiosity meets structure, where questions are answered not with more detail, but with deeper rules. It is the boundary that keeps extremes contained, allowing the vast, calm cosmos we inhabit to exist at all. Without these limits, there would be no gentle stars, no steady time, no quiet moments like this one. Everything you experience, space that feels solid, time that flows softly, energy that warms rather than overwhelms, exists because the universe chooses restraint over infinity, because it spreads what must be spread and seals what must be sealed. As you rest now, you are far from those violent scales. Energy around you is diffuse, gravity is gentle, time moves kindly forward. The deepest turbulence of reality remains buried beneath layers of distance, expansion, and law, doing its work silently so that calm can exist here. If this journey through the hidden architecture of the universe brought you a sense of wonder, perspective, or peace, I'm deeply grateful you spent this time with me. Thank you for listening, for slowing down, for letting these ideas drift through you at your own pace. You don't need to solve the universe tonight. You don't need to push any boundaries. The cosmos is steady, the limits are holding, and you are safe to rest within them. Good night.